In this tutorial, I'm going to talk about this Maxwell equation that we see right here. This is called often Maxwell's first equation in integral form. It talks about the electric field integrated over a surface. And we have a name for that. We call that whole thing here a flux. So the left-hand side, spoken in English, is the flux of the electric field through a surface whose differential elements are d sigmas. So for example, I could have a spherical surface. That's our typical surface that we will actually sometimes evaluate. And everywhere over the surface we can define little patches, which we would call a little d sigma. Relative to the surface, you can define a normal. That's the direction of d sigma. And at that point in space, that's some point in space, I'll emphasize that by saying that we could have a coordinate system with an origin way over here. These might be the x and y axes relative to that origin in a 3D space. And that place where that patch is located by some vector r. So at that location, I can think about the electric field at location r at some time t. And that electric field might be pointed in some direction like this. So that's the electric field E as a function of r and t. So I really want to get across the point that you have a normal to that surface there. The electric field does not have to be normal to that surface. It has whatever value it has, and I've drawn whatever imaginary shape I want to draw. But I can always talk about, for any closed surface that encloses a volume, I can talk about the total flux of the electric field through that surface, and that's how much of the electric field is pointing through that surface, in other words, in the direction of d sigma. And that sum, I want to emphasize that this is a sum. That sum is called the flux of the electric field through that surface. Now there's a physical law that says that that's equal to the integrated charge inside of that volume. And there's a fundamental constant epsilon naught there. So this thing here, which I'm going to put a box around, this is a physical law. And so there's only so much that we can ask, well, why is it true? It's a law. The electric field pushing through the surface in some sense is almost defined by how much charge there is inside the surface. Now, it also turns out that mathematically, as you've learned in earlier math classes, if I write any vector field E and I integrate it over any surface in exactly the same sense that I meant it last time, it's also true mathematically that's equal to a volume integral, and it's equal to this. It's the del dot E integrated over that volume. We're talking about the same exact volume here. The enclosing surface integral equals this integral over the volume. And you can go back into notes, I will not do it here, to talk about why this integral equals this integral. So let me put a box around this that you saw in Optics 287 and also in Math 164. That's a mathematical relationship. It's a relationship between an electric field and some particular derivatives of components of the electric field in space. And now what we emphasize is that the physical law for the flux of the electric field can be compared to this mathematical expression, which is also for the flux of the electric field and how it relates to a volume. Now we've got two different volume integrals that are equal. And if you have two volume integrals that are equal for any surface identically, it must be the case that their integrands are equal. So what I'm doing is I'm saying that this quantity has to equal this quantity. So now I get the the result, the divergence of the electric field is always equal to the charge density that's present at that location in space divided by epsilon naught. So this quantity here, del dot E, that has a name. I just said it once and I'll say it again. This is the divergence, or div, of this field. And I want to emphasize here that that is a local property. The flux was a sum. In other words, it was averaging over all the regions on this surface. Now we've got a very nice thing, which is we've got a divergence, which is a local property. It's the divergence of the electric field at a particular place. It's inside the integral. I've now pulled it out of the integral to get to this equation here. Which we'll call the name Maxwell 1, Maxwell's first equation in differential form. And to emphasize that we often want to think about this divergence electric field, I'm even actually going to write it that way, that the div of E is equal to rho, the charge density, over epsilon naught. Very similarly, for magnetic field, the corresponding equation, like this electric field equation, I will just make it appear. This is the equation for magnetic field flux. And the magnetic flux is always equal to 0. That's a physical law. And by very similar logic to what we've got up above, since the magnetic flux has to be equal to the integral of the divergence of the magnetic field, we therefore reach the conclusion that the div of the magnetic field simply equals 0. So now we've got Maxwell, and that's Maxwell's second equation.